sliding window median at massive scale. We will maintain the median over a stream of 10 to the 8 numbers with limited memory, and we will report latency and amortized complexity. The task: for each new element in the stream, output the median of the last W elements, called the sliding window. We cannot store the entire stream of 100 million values. We only keep state that scales with the window size W, not with the total length. The median splits the window into two halves. For an odd window size W, the median is the middle element when the window is sorted. For an even window size, it is the average of the two middle elements. Graphically, think of a balance point on the number line that has half the values to the left and half to the right. Naively, after each new element, sorting the W items costs W log W time, which is too slow. We need about logarithmic time in W per update. The classic solution uses two heaps, a max heap for the lower half and a minute heap for the upper half. The median is either the top of the heavier heap or the average of the two tops. We will simulate updates on a small window of size 5 to visualize the algorithm: an incoming element, a queue that remembers order for removal, and two heaps that split values below and above the median. Nothing will overlap. Each column has its own vertical space, and labels sit above or below with room. Let us insert values into the data structure while maintaining two invariants. 1. Every value in the low heap is less than or equal to every value in the high heap. 2. The sizes differ by at most 1. We show the window order on the left and the two heaps on the right. We will use a window of 5. Now we slide. When a new value arrives, the oldest leaves the window. We cannot directly remove an arbitrary element from a heap in logarithmic time. We use lazy deletion. We mark the outgoing value, and whenever it floats to the top of a heap, we actually remove it. Then we rebalance. The median is always the top, or the average of the two tops. The invariants are: 1. Every element in the low heap is less than or equal to every element in the high heap. 2. The sizes differ by at most 1. 3. When the total count is odd, the median is the top of the larger heap. When the total count is even, the median is the average of the two tops. These invariants are enforced after every insert and delete, guaranteeing a correct median. Each update does at most a constant number of heap insertions, heap pops, and size rebalances. Each is logarithmic in the window size W. Lazy deletion only charges the cost when a deleted key reaches the top, so its cost amortizes into the same logarithmic bound. Therefore, the amortized per update time is big O of log W. The memory is big O of W for the two heaps plus a small hash map for pending deletions. Latency model. A heap operation uses about log base 2 of W comparisons. If each comparison takes C microseconds, including memory access overhead, the update latency is approximately alpha times log base 2 of W plus beta microseconds. Here, alpha and beta are machine-dependent constants. The key point is that latency grows slowly with W. We never store the full stream of 100 million numbers. We only keep the current window. For an exact median, you must store all W elements. Suppose each stored value with overhead requires B bytes. Then memory is about B times W plus the hash map overhead for lazy deletes. This meets the limited memory constraint as long as W fits memory. Finally, the heaps approximate a dynamic split of the distribution. Conceptually, picture the histogram of the current window with the median cutting area into half. The two heaps store the left and the right halves. As the window slides, mass moves between halves, and the boundary, the median, shifts smoothly. Summary: a sliding window median over a massive stream is maintained exactly with two heaps and lazy deletion. The amortized time per update is big O of log W, and the memory is big O of W. Latency grows with log base 2 of W. The method avoids storing the full stream and satisfies limited memory constraints while delivering the median for each step.